This section on your mind map is linking to energy, and there are two kind of key sections to this. The first one is how we have the ability to calculate energy, and this tends to be an area that is quite poorly answered. Okay, so I'm going to talk a bit about the method, how you do it, and then how you would actually calculate the amount of energy released. And we'll look at how you can convert that into energy released per gram. So what you tend to do, if you want to work out how much energy is being released by a fuel, is you'll use something called a spirit burner. And above the spirit burner, there will be a beaker or a copper can, depending on what you're using, suspended above, where you'll put a specific amount of water into the beaker, and you will need a thermometer in order to work out the temperature. Now, in terms of steps, what you do is you measure the temp of the water at the start. You weigh the fuel in your spirit burner at the start, because what you want to have the ability to do is to work out how much fuel you have used. You then light the fuel in your spirit burner, and then for a particular temperature rise, okay, it depends, it might be 10 degrees Celsius, it might be 20 degrees Celsius. You let the temperature increase up to a specific temperature. So you're going to have to measure that using your thermometer, and then you blow out the flame and you will re-weigh your fuel. Okay, so you take the temperature of the water at the start, that'd be around about room temperature. Make sure you've weighed the fuel in your spirit burner. You're going to light your fuel, let the temperature increase up to a specific amount, maybe 10, 15, 20 degrees, could be up to 40 degrees. And you're going to blow out the flame and then re-weigh the fuel. Now, the reason why you re-weigh the fuel is that you want to know how much fuel you used to release a particular amount of energy. And there are two bits of information they'll generally give you on questions. The first one will be the temperature change. And you'll also be given the fuel change. So basically how much fuel had actually burnt. They will generally give you the equation, and the equation is energy, which is in joules, and that's the energy that's released and transferred to the water, is equal to mass times the specific heat capacity multiplied by the temperature change. Now, what a lot of students get confused about to start with is the mass. Some people think it's the fuel change, so how the mass of the fuel has altered from the start to the end of the experiment. What it actually is the mass of the water. And that's the water that you were heating up in the previous diagram. Now, working out the mass of water is actually very, very easy. If, for example, you used 100 millilitres, that is equal to 100 grams. If you use 200 millilitres, that would be equal to 200 grams. So basically 1 millilitre is 1 gram. So the mass of the water is really important. The specific heat capacity will be given to you, okay, in the actual exam paper, and that's usually given as 4,200. The temperature change will be dependent on the data you're actually given, but the temperature change will be difference between the starting temperature and the end temperature. So let's say it started at 20 and went up to 40, the temperature change would be 20 degrees. So let's say we had 100 grams of water, and we multiply that by the specific heat capacity, and we multiply that by 20. that will give us how many joules of energy was actually transferred to the water. In a lot of questions, they don't just want you to work out how much energy was transferred, they actually want you to know how much energy was transferred for every gram of fuel, basically joules per gram. If that's the case, you then need to look at the change in the mass of the fuel. Let's just say that the energy transferred was 10,000 joules. And the change in fuel, we started, let's say, at 5.6 grams. And the fuel, once it had burnt, there was 4.8 grams left. So that means that the fuel dropped, if you work out the difference between those values, the fuel dropped by 0.8 grams. In order to work out joules per gram, it is no different to joules divided by grams. So if you had worked out previously that 10,000 joules of energy had been transferred, you divide it by the mass of 0.8, and that will give you the answer as joules per gram. So the questions tend to be data-based, and it's about looking at the data to ensure you have the temperature change. You will know the mass of water generally from the diagram they give you. Okay, so it will tell you how many millilitres had actually been used. And then it's important to look at the mass difference for the fuel, divide the energy calculated in the first part by the mass of the fuel burnt, which will give you an answer in joules per gram. The energy section also includes looking at two types of chemical reaction. All reactions divide into exothermic or endothermic. Endothermic reactions are reactions that actually get cooler because they absorb energy. That may sound a little bit weird, that something absorbing energy will cool down, but once you understand what the energy is used for, okay, it makes a little bit more sense. Exothermic reactions are reactions that get hotter, and that's because they release energy. Exo is like external, the X part, okay, releasing energy outside, externally. When you look at any chemical reaction, okay, as we've talked about before, you start with reactants and you basically produce products. Let's just say a nice simple reaction. A reactant with B produces chemical AB. So when we actually look at the chemicals involved, let's say this is A, that represents B, and this represents AB. What we've got is two things happening. Inside the reactants, in order to produce the products, the bonds between the atoms within those compounds have got to break. So reacting is all to do with bonds breaking. When the new products are formed, the bonds are made. So forming a new product is all about making new bonds between atoms that didn't used to be bonded together. So these atoms all have to break apart, they rearrange, and then new bonds are formed between different atoms. Bonds breaking is what is called an endothermic process. And that basically means that energy is taken in. So bonds breaking is endothermic because energy is taken in. When the new bonds are made, it's an exothermic process. And that's because of the fact that energy, when bonds are made, is actually released. So when you break bonds, energy goes in to break those bonds, and when the new bonds are made, energy is released as those new bonds are formed. Bond breaking endothermic, bond making exothermic. Reactions are also described as endothermic or exothermic. So let's start looking at exothermic reactions. In the case of an exothermic reaction, there is a difference between how much energy goes in to break the bonds within the reactants compared to how much energy is released when the new bonds are made. So let's say we have chemicals C and D reacting to produce a new product. So there's our C, there's our D, and there's our new products that we produce. So what has to happen is energy has to go in to break these bonds. That's our endothermic process. And then energy is going to be released when these bonds are made. That's an exothermic process. However, the overall reaction in this case is exothermic. And that means that overall, we have energy released. And that causes the reaction to get hotter. So if we compare the amounts of energy that needs to be taken in compared to how much is released, there is a difference. In the case of an exothermic reaction, a small amount of energy is taken in to break the bonds between the reactants. In comparison, a lot of energy is then released when these new bonds are made. So because there is a difference this much between how much has gone in compared to how much is released, because more energy is released in comparison, the reaction will actually get hotter. In the case of endothermic, the opposite applies. Overall, if you remember at the start, we basically said that energy, in the case of endothermic, is absorbed. And this actually cools the reaction down. So if we say chemical E and F reacts to produce a product, EF, there's our reactants and there's our products. Again, energy's got to go in to break the bonds, and energy will be released when these new bonds are made. So again, this is an endothermic process because energy goes in. That's an exothermic process because energy is released. But overall, this particular chemical reaction is endothermic. And again, it's the difference between how much goes in to break the bonds compared to how much is released when the new bonds are made. So in the case of an endothermic reaction, lots of energy goes in to break those bonds, okay, between the reactants' atoms. However, when the new products are made, only a tiny amount of energy is actually released. So in comparison, you are absorbing this much more energy into the reactants to break the bonds with only a very, very small amount. So overall, there is more energy absorbed, which will cool the surroundings down because the energy goes into those reactants in order to actually break those chemical bonds.